All right, so continuing on then, we had showed this before last time. Let me hit the code lights here to get a little less light on there. There's M83, Charles, number 83 on Charles Messier's list of things that are not comets. Famous spiral galaxy, there it is in 21 centimeter radiation. So again, 21 centimeter radiation is emitted by the electron in a hydrogen atom in the ground state, flipping its spin relative to the proton, and that very low energy transition corresponds to 1430 megahertz, or 21 centimeters in wavelength. It's a dipole, electric dipole forbidden transition. Quantum mechanically speaking, it's a magnetic dipole transition. And as a result, it has very low probability of occurring, which is why, on average, a hydrogen atom in the upper state, the spins, I forget which one it is, parallel or anti-parallel, it's higher. Yeah, in the parallel spins, higher energy configuration, on average, it's like 11 million years before it would be like, yeah, I guess I'll flip down to the lower energy configuration. And so as a result of that, it's much more readily observed in the interstellar medium, where the densities are extremely low, so that you don't have nasty collisions or whatever disturbing your hydrogen atoms before they can make the transition. And so we use it to map out atomic hydrogen clouds in the interstellar medium, both in our galaxy and in external galaxies. And we do see that just like hot young stars are clumped, if you will, along spiral arms of galaxies, so is gas and dust tend to be concentrated along them. And when we talk about galaxies, we'll see stars themselves actually are not particularly concentrated in the spiral arms, but they're sites of active star formation. And while the rarest types of stars are O and B type stars, they're the ones that form the least, they're loud as hell in that they are very luminous. And so one O star can be as luminous as, thousands of suns. And so the spiral arms of galaxies look blue like that because of hot, young O and B type stars that were born in the lovely pink H2 regions that are also strung along the spiral arms. The typical, like for our galaxy, one rotation of our galaxy takes about 225 million years at the sun's distance from the center. Turns out that the spiral arms are density waves. They're not material that stays within the spiral arms. And those density waves, as we'll talk about shortly, move through the disk of the galaxy at a different speed than the star's gas and dust do. So a given star like the sun is sometimes inside of a spiral arm and sometimes in between spiral arms. How long does the sun live on the main sequence, roughly? What will be the sun's lifetime, roughly speaking? Like 10 billion years. Very long compared to the rotation period of the galaxy. How old is the sun now? About 4.56 billion years at this point. So the sun has made many rotations of the galaxy in its lifetime, because it makes about 4 every billion years, and so it's had time to like 16, 17, 18 spins around the center of the galaxy. And so sometimes the sun is in between spiral arms and sometimes it's within a spiral arm. And that's true in general for lower mass stars. And if you use a filter that doesn't let through blue light, it's a lot harder to see the spiral arms because the lower mass stars are more uniformly distributed within the disk of the galaxy. But the O and B type stars are clustered along the spiral arms because an O-type star, for example, lives a few million years. That is very short compared to the time that it takes the galaxy to orbit. Well, that it takes a typical, what should I put it this way? It depends on how far you are from the center, but we're talking about 200-ish million years for a star to orbit the galaxy. If a star is only going to live about 5 million, 10 million years before it blows itself up as a supernova, like these O and B type stars, then they explode before they have time to get very far from where they were born. And as a result, they are concentrated along the spiral arms. Here is 21 centimeter radiation from our own Milky Way galaxy. Now this makes it look like the map was made from the outside, but no, this was inferred from looking at the Doppler shifts of the 21 centimeter radiation. Because if a cloud is moving towards us, it's blue shifted to a little shorter than 21 centimeters. It's moving away from us, red shifted. And so details are in the later chapter in the book. Radio astronomers are able to map out the distribution in space of the atomic hydrogen clouds from the fact that we know that the galaxies, everything is orbiting. And so you can use that to model where everything is, because the Doppler shift of a given cloud is going to depend on how far it is from the center of the galaxy and where we are relative to that cloud, relative to the center of the galaxy. And so you can use those Doppler shifts to systematically map out the locations in space of all those clouds. And so we can do that, and we can see that, yeah, you can see hints of the spiral arm structure of our galaxy from within by looking at this 21 centimeter radiation. And very long wavelengths means that it passes right through interstellar dust. We cannot see very far within our galaxy at visible wavelengths, because in the disk of our galaxy, you get beyond a few thousand light years, about 10,000 light years or so, and interstellar dust makes it impossible to see anything beyond that. So we cannot see directly to the center of our galaxy. We can see the direction there, but really we can only see kind of to the next spiral arm in one direction and to the next spiral arm out in the other direction. But at 21 centimeter wavelength, you can see all the way across the galaxy, because that radiation can pass pretty much unimpeded through the disk of the galaxy. Yes?
When we look at, like, if we're in a really dark skies and we're seeing roughly throughout the sky, that really big bright clump, is that towards the center of the
Yes,
galaxy?
the really big bright clump that's in the direction of the constellation Sagittarius is the galactic bulge at the center of our galaxy that sticks up above and below the plane of the disk of our galaxy, and we can see that bulging out from where we are. Yes.
So we're kind of seeing it from sideways.
We're seeing it from sideways, yeah. We live within the disk of our galaxy, and what we see as the Milky Way on the sky is the disk of our galaxy seen from within. The faint glow is stars that are too far away for us to, with the eyes, resolve them individually, and so they just make up what looks like just a faint band of milky glow across the sky. The word galaxy comes from the Greek word for milk. So it was reminiscent to the ancients of like milk, essentially. And the stars we see in the night sky as individual stars, those are just stars that are close to us. Because the disk is, we're within the disk. So if we look away from the direction of the disk of the galaxy, we see relatively nearby stars that are above and below us, so to speak, relative to where we are within the disk of the galaxy. But as we look further out, we see just the disk of the galaxy, and many, many stars blending together make the Milky Glow, and there are dark bands within it that are interstellar dust clouds that obscure the view to more distant material. It's interesting that the native peoples of Australia, in their sky lore, the sky is, they're in the southern hemisphere, where you get the best views of the direction to the center of our galaxy, because Sagittarius and Scorpius are southern constellations, and that's where the center of the galaxy is. So they get wonderful views of the night sky and the part of the Milky Way that is the direction towards the center. The skies are so dark there, even in the outback, even now, and all across the continent before, that they actually name the dark patches. Those are distinctive enough features of them that they gave names to the dark patches. Whereas other cultures tend to be all about naming collections of stars, constellations or whatever. So, fun facts there. Okay. What other questions do you have? Okay. Components of the interstellar medium. So, H1 clouds, that's what we're talking about where we can see 21 centimeter radiation. You need atomic hydrogen for that. Molecular hydrogen, H subscript 2, right? Molecular hydrogen clouds are not going to exhibit the 21 centimeter line because it's specifically caused by an electron in the ground state of the hydrogen atom, not a hydrogen molecule. Temperature, 50 to 150 Kelvin, right? It's very cold by human standards. What is room temperature, roughly speaking, in Kelvin? What's that? Yeah, around 300 Kelvin, 290 Kelvin or so. So you wouldn't want to be somewhere where it was 100 or 150 Kelvin out. Very, very cold. Density, atoms per cubic centimeter, about 1 to 1,000 atoms per cubic centimeter. The gas is neutral hydrogen, because it's H1 clouds. 1 to 1,000 atoms per cubic centimeter. Is that a lot, or is that practically a vacuum? Well, what about our atmosphere? Any clue how many atoms per cubic centimeter in our atmosphere, roughly speaking? A lot, yeah. It's like 3 times 10 to the 19th power atoms per cubic centimeter around where we are in this room. And so, that ain't nothing, right? 1 to 1,000 atoms. That's a really good vacuum by terrestrial standards. But by the standards of the interstellar medium, that's relatively dense, right? It's much denser than the so-called intercloud medium. So by volume, much of the interstellar medium is what's called the intercloud medium. Diffuse H2 ionized hydrogen that is in between the more clumped clouds of interstellar material. Density is a lot lower, 0.01 atoms per cubic centimeter. The temperature, though, is 1,000 to 10,000 Kelvin. If you think about it, well, there should be, roughly speaking, pressure equilibrium between different parts of the interstellar medium, because otherwise, if the clouds were at higher pressure than the surrounding intercloud medium, well, they expand outwards because of that. Vice versa, if the intercloud medium had higher pressure. So roughly speaking, if you took the density times the temperature, they should be about the same. So in other words, it has to be true in equilibrium that the intercloud medium better be at a higher temperature because it has so much lower density than the H1 clouds do. The gas, why it's partially ionized. Then you have coronal gas, temperature of 100,000 to 1,000,000 Kelvin, densities of only 10 to the minus 4 to 10 to the minus 3 atoms per cubic centimeter. Highly ionized, and that comes from supernova explosions. And shock waves from the heat up material to those very high temperatures. And then there's molecular clouds, which are the densest parts. Temperatures of 20 to 50 Kelvin typically, densities of 1,000 to 100,000 atoms per cubic centimeter. And there the gas is in the form of molecules. Those are denser parts where the hydrogen atoms and other atoms, they're packed densely enough, very undense by terrestrial standards, but densely enough that they'll collide and form molecules. Two hydrogen atoms bump into one another and form an H2 molecule. It's the molecular clouds that are the sites of star formation. An H2 region is a portion of a giant molecular cloud where star formation is occurring. What questions do you have at this point? Push the magic button. So, how do we study giant molecular clouds? We can use radio telescopes to study them. However, while far and away the major component of a giant molecular cloud is hydrogen molecules, H2, H2 is a very poor radio emitter. And the reason for that is that it is a symmetric molecule, right? It's two hydrogen atoms, so it's symmetric. And so that means that the electrons have no reason to quote-unquote spend more time around one hydrogen than the other. Quantum mechanically, it's in other words, the electron cloud is distributed symmetrically between the two ends of the molecule, so it doesn't exhibit any permanent dipole moment, any permanent charge separation, where one end is positive and the other end is negative. And it turns out that if you made like a classical model, if you have a dipole, right? So in other words, positive charge on one end, negative charge on the other end. If you have a dipole and that is either vibrating or rotating end over end, that will give off electromagnetic radiation because accelerating charges radiate, and if it's vibrating, the two ends, plus and minus, are accelerating because they're jiggling. If it's rotating, they're accelerating because circular motion is accelerated motion. And so you get what's called electric dipole radiation as a result of that. And that's true quantum mechanically too, even though you can't literally interpret it as classical vibration or rotation when it's quantum mechanics, but it's still true that molecules can undergo quantum transitions that correspond to them changing their vibrational energy levels or their rotational energy levels. And one of the exciting homework problems you do this time around will be to look at different isotopes of carbon in carbon monoxide molecules and figure out how their moments of inertia differ from one another and what that would imply about the radio frequencies that they're able to emit. So that'll be fun. But in any case, for now, what I want you to think of then is, in order for us to see radio waves, we need polar molecules, ones that exhibit charge separation. So for example, carbon monoxide. Don't breathe it, but if you're a radio astronomer, you can use it to study. It's probably the most important tracer molecule for studying the distribution of gas in giant molecular clouds, and we infer that the hydrogen is distributed in the same way. In other words, there's no particular reason to think the CO should be distributed differently than the hydrogen. So if you know how many hydrogen molecules there should be for every CO molecule, you can infer from your CO radio maps how dense the hydrogen is in different parts of the cloud, and the hydrogen will carry most of the density. So CO is polar because have you heard of like electronegativity in chemistry before? Oxygen is much more electronegative than carbon is, and so in CO the electron cloud is more strongly on the oxygen side than it is on the carbon side, and so the oxygen end has a net negative charge. The carbon side has a net positive charge, so as a result, you have a dipole. And so the CO can vibrate and rotate in the quantum mechanical way and produce radio photons. And so studying that emission with radio telescopes allows us to map out giant molecular clouds. So here is the giant molecular cloud complex that is in the direction of the constellation Orion. And there's the Orion Nebula. It's an H2 region, which is a small portion of that giant molecular cloud. Horsehead Nebula, a small portion of that giant molecular cloud. Questions? They tend to be a couple of hundred parsecs across, so that's what we call giant molecular clouds. They're pretty large. Here is an X-ray image of Cygnus showing hot coronal gas associated with a supernova explosion, which created a shock wave that heated the gas behind it and produced the Cygnus superbubble. I like that name. It's a Cygnus superbubble. We seem to be living in a bubble like that. There seems to have been a supernova that blew a bubble in the region that we live in. We're in an underdense region of the interstellar medium that is very hot, filled with coronal gas, blown by a supernova, a bubble blown by a supernova sometime. Here's the Orion Nebula. I should have put this one earlier in the presentation. the lovely pink color, right? Because of what spectral lines of hydrogen? Why, the Balmer series lines, of course, which are the ones that are transitions from higher energy levels down to n=2, and n=3, n=4, n=5, and n=6 give the visible lines, 7, 8, 9, 10, and so forth, on n=2 are ultraviolet, so our eyes don't see them. Why, let's review. n=3 to n=2. What color is that spectral line? Which one is that?
Red.
That's the red one. Yep, that's the lovely red one. 4 to 2. Next wave, the next shorter wavelength. Why, that one is teal or aquamarine or bluish green or whatever you want to call it. That one's good for arguments. Is it more blue or is it more green? And maybe you too can be like my wife and I, who had an argument, stupid, I think I've told you this, stupidest argument we've ever had, because we were arguing whether this particular ladybug was, if her shell was more red than orange or more orange than red. This is subjective, this stupid argument. We're actually getting mad at each other. Stupid. We laugh about it now. We weren't laughing at it at the time because we were stupid. Anyway, and why these two transitions, you might even be tempted, if you want to live dangerously, to say that their color is, shut up! Yeah, indigo, yes, right. And they blend to make the lovely pink color. Trifid Nebula is another, this is one of those, you've probably seen this picture before. This is a picture people have seen and they don't know what it is, right? Just like many people, they'll hear a classical music piece and they'll be like, oh, I know that one. Oh, what's it called? I don't know, I just know I've heard it before, right? There's lots of photos of the interstellar medium where everybody's seen it before, but unless they're like, you know, astronomer types, which everybody should be damn it. But anyway, everybody should be interested in the universe, even if they're not going to be astronomers. This is the famous Trifid Nebula, so called because it's kind of like divided into 1, 2, 3 portions like that. It's a combination of a reflection nebula, the bluish color, along with an H2 region. There's hot young stars in there, hot young O stars that are the source of the ultraviolet light that is ionizing the hydrogen, that is allowing the H2 region to do its emission thing. With the Orion Nebula, there's a group of 4 stars called the trapezium, 4 O stars in there. I think they're all O. There might be a B in there, I'm not sure. But anyway, the hottest of those is the one that's most responsible for ionizing the Orion Nebula. And through like if you look at it through a telescope, either a backyard telescope or even, you know, if you go like the Perkins telescope, the trapezium is lovely. You can see it there very nicely. Here, if you expose long enough to show the nebulosity, you overexpose the center. If you expose long enough to show the color of the nebula, you overexpose the center, and so you can't see the trapezium. But through the telescope, it's lovely. You see the trapezium and the ethereal glow of the surrounding nebulosity. Nebulas are good for making you want to use the words ephemeral and ethereal, which is perfect descriptions for what it looks like through the telescope. So we said that giant molecular clouds are star-forming regions, and in fact, okay, we're gonna put some quantitative details into this in a bit, but for now, suffice it to say that in order for a star to form, well, let's see, a star is a battle between the inward force of gravity and the outward push of pressure, right? And if you're in an interstellar cloud and pressure and gravity are in balance with one another, it stays a cloud. To have a star form, you need to have something tip the balance in favor of gravity, so that gravity is stronger than pressure within the cloud, and it can begin to collapse as a result of that. Well, best way to do that is to have a shock wave pass through a portion of a giant molecular cloud. A shock wave will compress the material. You can give it a squeeze, and you can get a situation from that where the squeeze, well, the squeeze increases the pressure and the gravity too, but a shock wave can give it a squeeze such that after the shock wave goes through, you've got a region where gravity exceeds pressure and star formation can begin there. So here's a Hubble Space Telescope image of shock waves within the Orion Nebula. Quite lovely there. So there's labeled some shock waves. What is a shock wave? So a shock wave is created when an object moves faster than the speed of the waves that it emits. As a result of that, the waves can't get out of its way, so to speak, and so their energy piles up into a shock wave. So, have any of you ever heard a sonic boom before? Yeah, I mean, it can break glass. You make a sonic boom, you can have that by, if you have a jet aircraft that is capable of exceeding the speed of sound, then when it flies through the sound barrier, so to speak, it can punch through sound waves that have built up in front of it, and that produces the sonic boom. So I'll play that animation that I link on the bottom there in a minute. But the idea is start with water waves. If you've got a stationary boat and it's just bobbing up and down, and it's always appropriate for me to say that given my first name. So here I am, I'm in the water and I'm bobbing up and down like bobs tend to do. And ripples spread away, nice and evenly like in the stationary boat illustration there. But if the boat, or if I am moving along as I bob, well then we'll get a Doppler effect. In other words, it'll pile up the ripples in front and stretch out the ripples behind. If a boat moves faster than the ripples that it's creating in the water, then you get what is called a bow wave, where the ripples that it's producing can't keep up with the boat itself, and so you get what's called a bow wave from the envelope of all of those ripples. And if you are on the back of like a motorboat or a cruise ship or whatever, you'll often see like the bow wave spreading out in both directions behind it. It's because the ship is moving faster than the speed of ripples on water, and it produces a bow wave as a result behind it. Now have an airplane flying through the air. If it's flying slower than the speed of sound, well, the sound waves it's emitting can stay ahead of it, but you do get a Doppler shift as a result of that. But if the plane is flying faster than the speed of sound, then its sound waves are not able to keep up with it, and then you get a shock wave at the envelope of those sound waves. So now let's play this Flash animation. Flash is no longer supported. It was discontinued by Adobe in 2020, but there's an extension called Ruffle that still lets you play Flash. So I installed Ruffle on my browser here, and I'll have to jump out of here and go to the next tab where we will play this simulation. So first, I can change the speed of the source here. And so I'll play, and ooh, there's all the ripples coming out. Ooh, but now, let's get it moving. Right now, it's moving slower than the speed of sound. And so as a result of that, you just see a Doppler shift. It was piled up in front, wave crest stretched out behind. Right now, it's moving at 35.4% the speed of sound. Dial it up here, let's get to like, now we're going at like 93.4% the speed of sound there. Why the waves are having trouble getting out of its way, let's break the sound barrier. And so you see that phenomenon of this radiation's like in a cone behind it as a result of that. Ooh, So shock waves are regions of high compression because the material can't get out of the way, because pressure is relieved by sound waves traveling in a wave. But if you ran something through a material faster than the speed of sound in that material, then sound waves cannot carry the disturbance, carry the energy being imparted away from that area. And as a result, the material starts ramming together and compressing, and you get a shock wave as a result of that. And material that passes through the shock wave gets strongly compressed and heated as a result of that. Okay? Okay. What questions do you have? Yes?
This was from like 20 minutes ago, but on the slides, when you're on the like Cygnus slide, there was like the other really bright region, the loop or something. What is that?
Oh, the Cygnus loop?
Mm-hmm.
Yeah, that also shows up in visible light as well. Yeah, is it, yeah, let's see, yeah, I forget, but I think that's, I better look it up, I forget.
Because isn't there like the Cygnus black hole somewhere, like Cygnus X1?
There's Cygnus X1, yeah, but I don't think that's involved here. I could be wrong though, I could be wrong. Yes?
I looked it up and it says
Oh,
that
cool.
it's a large supernova remnant in the constellation shape.
That's the Cygnus loop?
Yeah.
Yeah, okay, cool, all right. So does it say anything about it having blown the super bubble? Because it doesn't look like it's in the right location to itself have blown the super bubble, but maybe it did, I don't know.
It does not say.
It did not say. And I feel like, does it have a picture of it? Because I feel like if I think I can probably Cygnus loop, everybody. So yeah, here's Chandra images. There's a Chandra X-ray telescope image, and I don't know what wavelengths these are, but look, it's the Cygnus loop, which is a large supernova remnant. So a shock wave is blowing a bubble around there too, and so heating of that material is why it glows at the boundary of it, because the compression of the interstellar medium is heating it up with ionizing gas, and so you get emission lines and all that kind of good stuff. Okay. Yeah. Oh, and I can't help it. I like duckies, and I just think this is too cute to ignore. Here's a duck moving faster than the waves it's making, and so it's forming a bow wave behind itself, just like a ship does. So there you go, super duck moving supersonically, well not faster than sound, but super ripply, I don't know what you can call it. Adorable. And I'm just imagining the little paddling underneath there. So, isn't that cute? I know. Yes. So a duck educating us about star formation. I like that. Thank you, Mr. or Ms. Duck. Yeah, there's a water feature in my condo complex, and so lots of ducks live there, and I get charmed by. For a couple of years now, we've had this male and female. I think they're probably the same ones that they hang out like in front of our place, and so they're just like. Yeah, and you walk up to them, you know, and I don't try to get too close, but they're like, you just walk away. And then they'll fly away, and they're following one another. It's so charming. Anyway, phenomena that can produce shock waves within giant molecular clouds, and thus trigger star formation. Why? We can have collisions between giant molecular clouds. So giant molecular clouds can collide with one another, and in the region where they're colliding, you can get compression that can initiate shock waves, that can initiate star formation. Embedded magnetic fields keep them from simply passing right through one another, right? Because they're very low density, and so you might think, well, why don't they just pass right through one another? But there is some ionization of the material on the outer parts of the clouds that is due to ultraviolet light from distant stars and X-rays from distant stars hitting the material at the periphery of the cloud. And so that's a source of free electrons and ions that can then help produce and be entrained by magnetic fields within the clouds. I'll have a slide that illustrates the idea momentarily. So collisions between giant molecular clouds, and as we'll see, that will tend to happen along spiral arms, which is why spiral arms are where star formation tends to happen, where you see those H2 regions that are the stellar nurseries that themselves are parts of giant molecular clouds where star formation is occurring. Stellar winds from hot young O and B type stars can compress the surrounding interstellar medium, producing what's called self-sustaining star formation. I'll show a slide that shows that in some more detail after the break as well. But the idea there is that once star formation begins, then it tends to be quote-unquote self-sustaining because supersonic winds traveling faster than the speed of sound in the surrounding interstellar medium, can generate shock waves as they spread into the surrounding cloud, and that can initiate more star formation. So stars forming can beget more stars forming. Supernova shock waves. So when a high-mass star explodes as a supernova, it flings out a lot of material that is moving supersonically and produces shock waves in the surrounding material. And in fact, we have good evidence that we owe our existence to that. The sun seems to have been born because of a shock wave from a supernova that blew up just before the sun was born, that compressed the material that later formed the sun and the planets. And the evidence for that is that there's a famous meteorite called the Allende meteorite, named after the town where it fell. And analysis of it shows there's a high abundance of an isotope called magnesium-26 in it. And magnesium-26 would come from the decay of aluminum-26, which is an isotope that would be produced in supernova explosions. So this thing is enhanced in magnesium-26. There's more magnesium-26 abundance than you would expect, and that would be explainable by aluminum-26 from the material ejected by the supernova getting embedded within the gas and dust that eventually formed the solar system, and it would decay into magnesium-26, would then show up in the Allende meteorite. We don't see it on Earth because, Earth is mixed and geologically active, and it used to be melted and all this kind of stuff. But with a meteorite, you're seeing primitive material. You're seeing leftover planetesimals from the solar system's formation that hasn't been processed in type of meteorite called carbonaceous chondrite. And the Allende meteorite is a carbonaceous chondrite. So it appears that we owe our existence to a supernova which blew up good and actually caused the collapse of the cloud of gas and dust that formed the sun and our planets, and presumably also siblings. The sun had siblings when it was born. They've wandered apart from one another now, but we've had siblings. And then finally, giant molecular clouds passing through spiral density waves, which in fact causes collisions between GMCs. Really, the last thing in the list there is really directly tied to the first one, because you'll get more collisions when giant molecular clouds pass through spiral density waves. And I know you can't wait to hear more, and so while in a few minutes you will, unless you're Kayla, and then you have to wait a while. But, it just gives you something to look forward to for the rest of the day. Alrighty, let's say a bit more about all of this. So, self-propagating star formation in a GMC. What's a GMC? Not a pickup truck, it's a giant molecular cloud. Yeah, because you get tired of saying giant molecular cloud all the time. Yeah, not General Motors Corporation in this context. Giant molecular cloud, self-propagating star formation. So the idea is that, we have a young cluster being born within an H2 region, a future open cluster like the Orion Nebula today, as I said, it's part of a giant molecular cloud, and the hottest stars in there produce stellar winds, which can have the effect of impinging supersonically on the nearby parts of the giant molecular cloud. That can then cause decompression that can produce new star formation. And so this keeps going. In other words, this region right here is going to turn into a full-blown H2 region down the line that can then continue material forming stars over here. So it can start to eat its way through the giant molecular cloud. So it's self-propagating star formation. And then here's a photograph of like an O-type star and several more solar-type stars nearby that are thought to have had their formation triggered by winds from the more massive star there. So I think that's pretty cool. And then meanwhile, you can see on the left, right, there's an old cluster where now the gas has been blown away and you just left with the star cluster itself. And there's an even older cluster, so on and so forth. Meanwhile, so there are clusters. Open clusters are groups of stars that have formed, and they have enough mutual gravity to hold the cluster together. So the Pleiades is an example of a star cluster. There are also associations where the total mass of the stars isn't large enough that their mutual gravity will hold them together. So they form together, but then they'll drift apart from one another because they're moving too fast for their mutual gravity to hold them together. And so you call that an association. The sun was probably born in an association. That's why it's not a part of a cluster now. There are clusters that are older than the sun is. The sun is not part of a cluster, so it was most likely born in an association. This is a photo of the R1 Canis Majoris Association. And so the H2 regions in this image are lit up by O and B stars in the R1 Canis Majoris Association. And that's a group of stars whose formation appears to have been formed by the passage of a supernova shockwave. And something very similar to this is thought to be how the sun was born. The sun was born as a star in an association whose formation was triggered by the passage of a supernova shockwave a little more than 4.6 billion years, like about 4.6 billion years ago, basically, right before the sun formed. So thank you, ancient supernova, for causing the solar system to form so that we could talk about the formation of the solar system and existing and all that kind of good stuff. So I think that's pretty cool. Back again to a photo we've seen before, number 83 on Charles Messier's list of things that are not comets, that spiral galaxy, just to emphasize again that spiral arms are lit up with pink H2 regions, and they're blue. They tend to look blue, whereas the bulge at the center of a galaxy tends to be reddish in color, because different types of stars are producing the light. The blueness of spiral arms is from very luminous, very rare, but very luminous O and B type stars that were born in them from H2 regions. On the other hand, the bulge is much older, and its light comes mostly from old low-mass red giants, and so it gives it a more reddish color like that. So, the idea is, and we'll explain some more about this in a minute, as I mentioned before, you might at first imagine that, the galaxy certainly has to be rotating, right? Otherwise everything would just fall into the center. So then the question becomes, well, are the spiral arms kind of like material spiral arms? In other words, once you're in a spiral arm, you stay in a spiral arm, or not? And the answer is not. They are density waves that travel through the disk of the galaxy, enhancements in density that travel through the disk of the galaxy at a different speed than the star's gas and dust. Where we are in our galaxy, the sun and nearby stars are moving faster around the center of the galaxy than the spiral arms are. So in other words, the sun continuously will catch up to spiral arms from behind, pass through them, move ahead of them, and then go chasing after the next spiral arm along the way, so to speak. So that leads us to the next figure, which shows this idea of we've got fast motion of interstellar gas and dust passing through the spiral arm. It's compressed there, and that compression produces star formation, because in particular, giant molecular clouds bump into one another in spiral arms more frequently, and those collisions can produce shock waves that can cause portions of them to begin star formation, and so you get hot OMB stars with H2 regions. Okay, so what questions do you have about this picture? Because I'll show kind of a more complicated picture in a minute that shows more directly what is going on. So questions about this picture at this point? Okay, gonna push the magic button. Okay, so here's a figure from chapter 25, actually. It's further on in the book about galaxies. So, and we'll revisit this concept later. But as I mentioned, spiral arms are actually density waves that travel around the disk at a different rate than the stars and the interstellar medium. So, it turns out that interactions between stars, gas, and dust, and often passage of other galaxies near a disk galaxy like our own, can produce a situation where the orbits aren't actually circular, they're oval. It's not even really ellipses, they're oval. So imagine, this is supposed to be the disk of a galaxy with oval stellar orbits, and we could have enhanced how oval they are to make it more clear what's going on here. Oval stellar orbits with their major axes aligned don't produce a spiral pattern. They could produce the bar in the center of a barred spiral, but first just picture this, that for whatever reason, you got a bunch of these oval orbits of stars and gas and dust. So imagine, lots of stars and gas and dust, they're on this orbit. Other stars, gas and dust on this orbit, this orbit. If the major axes are aligned, then there's no particular pattern. But if, and one can show that you expect this to happen, that in a disk galaxy, there's an instability that tends to produce this situation. If the major axes are systematically inclined to one another from the center to the edge of the galaxy, do you see the spiral pattern in there? Right? So, spiral pattern, okay? Now, if all the stars and gas and dust that are on these orbits, so remember the ovals are the actual orbits of stars, gas, and dust, right? So imagine stars and giant molecular clouds all strung out along each of those orbits. They're all strung out along each of those orbits, pretty evenly distributed along each of those orbits. If the orbits stayed in this configuration, the spiral arms wouldn't be going anywhere. They would just be kind of stationary, but it would still be true that, okay, here's stars, let's say everything's orbiting counterclockwise, here's a star or a gas cloud. Well, when it swings around to here, it's closer to nearby orbits in a region that is denser because everything is piled up there, and then it moves along and it's in a less dense region again. If this were the case, it would be the case that sometimes the sun, say it's right here, the sun is sometimes in a spiral arm, sometimes not in a spiral arm. But I said that there are density waves that pass through, that move around the center of the galaxy at a different rate than the stars, gas, and dust. And that is in fact the case. So imagine, if you will, and I wish I had an illustration of this, but I hope you can visualize this. Imagine that over time, the major axes are also slowly precessing around. So in other words, imagine like this orbit right here. If it stayed fixed in place, a star would just keep going like this around the center of its galaxy. But if the major axis is slowly precessing around, it makes like a spirograph pattern. Do you know what a spirograph is? It's a toy where you, right? So it would do this. It would be like, see what I'm doing here? Where the major axis, the long axis, keeps shifting its location in space. Like that. So imagine all of the major axes slowly, the directions of the major axes slowly turning around the disk of the galaxy. Then the whole spiral arm pattern would rotate around the disk of the galaxy. And that's essentially what happens. The whole spiral arm pattern rotates around the disk of the galaxy. And stars, gas, and dust are moving in the orbits. They keep catching up to and passing through the spiral arms as a result of that. Okay, so do you think you're picturing what I'm talking about so far? That's this basic idea. Okay? So, why would giant molecular clouds tend to collide within spiral arms? Because of this. Here's a giant molecular cloud. Here's a giant molecular cloud. Right now, they're far apart from one another. They're not colliding. They're just moving along their orbits and naturally getting closer together as they approach the spiral arm, because the spiral arm is there because of the fact that the orbits are closer together in that region. So in other words, la 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 la, oh, excuse me, shockwave, shockwave. Let's start some star formation here. And so you get star formation because of the fact that material naturally piles up in the spiral arms because it's where orbits are closer to one another. And so giant molecular clouds are going to collide and initiate star formation preferentially within spiral arms. Hence they're lit up with hot young O and B stars and lovely pink H2 regions as a result of that. And the blue stars stay in the spiral arms, if you will. They're concentrated there because they blow up before they leave where they were born. They don't live long enough to go very far. They blow up close to where they're born. They only live like a few million years, and it's like a couple 100 million years to go around the galaxy as a whole. So they blow up near where they're born, and so we see them. The spiral arms are lit blue because those blue stars that are forming there don't live long enough to get away from them. Question?
Oh, what would be causing the inclination of the major axis?
Yeah, so it turns out that I don't think we'll have time to go over this in class, but there's a nice mathematical model that's described in a later chapter where you show that there is a natural instability that causes this to tend to happen. In other words, there's an instability such that if another galaxy passes nearby, its gravitational influence will disturb the disk of the galaxy. And once you start this happening, it tends to grow. The interactions of the stars, gas and dust with one another, tends to enhance this phenomenon if you start it a little bit. That's why it's an instability. And so I can't give a simple, quick explanation, but it turns out that there's a natural instability that once this starts, it gets enhanced as a result of that. Hope that's a good enough explanation, or at least you'll top. If you want to know more, I got it in my notes in the galaxy chapters, and then there's also the book next month. It's actually pretty fun. But we've got so many things we can talk about. What other questions do you have? Okay. Yeah. All right. Where are we at? Okay. So let's talk about. Remember, we said that. Well, I'll go over this in more detail later, but here's this big picture. We'll say it in more detail. So, and I've mentioned this before. The idea is, with a star, For it to form, the cloud has to have gravity has to exceed pressure so that it can collapse. Initially, the collapse is in free fall. In other words, the pressure in a cloud that typically starts to collapse, it's become true that the pressure force is much weaker than the gravitational force. So a while you get free fall. Essentially, everything is just falling under the influence of gravity. But as it does so, the density and opacity increase, and eventually it gets to the point where it can start trapping its own radiation, and that heats it up, and pressure kicks in and slows the collapse down. And at that point, you've got something that you could really call a protostar, which is being powered by gravity. It's converting gravitational potential energy slowly into thermal energy and radiation as it shrinks. So protostars are not nuclear powered, they're gravity powered. And when the sun was a protostar, its luminosity was much larger than its main sequence luminosity. Its luminosity was more like it'll be when it's a red giant, except that it was emitting in the infrared as opposed to a lot in the visible when it's a red giant. So protostars are gravity powered. So the protostar keeps shrinking and heating and shrinking and heating. And if the core reaches about 10 million Kelvin, why that's hot enough for what to start occurring. 10 million Kelvin is the ignition temperature for hydrogen fusion. Yeah, hydrogen fusion. So if the mass of the star is more than about 80 times the mass of Jupiter, and the sun's mass is about 1,000 times the mass of Jupiter, so it's way over that limit, but the lowest mass stars are about 80 times the mass of Jupiter, then the core reaches 10 million Kelvin, and the proton-proton chain begins, or if it's a more massive star, it would be in terms of the CNO cycle. Either way, hydrogen fusion starts. Now you've got this nuclear source of energy that can keep the core hot and under enough pressure to support the weight of the overlying layers, and a star is born. It stabilizes, it stops collapsing because nuclear fusion is lit in the center, and a star has been born as a result of that. So that's like, look, ignition! And then the new star settles down on the main sequence, burning hydrogen in its core. It becomes a ZAMS star, a zero-age main sequence star. So that's, in a nutshell, what a protostar does. It starts out in free fall. Then, as it becomes dense enough, it becomes optically thick to its own radiation, starts trapping its own radiation, and as a result it gets hotter and the pressure rises and slows the collapse down. So then there's a period where it's what we would call a protostar, powered by gravity, and if the core gets hot enough, and it takes about 80 solar masses or more for that to happen, then hydrogen fusion ignites and it becomes a star as opposed to a protostar. If you are less than 80 solar masses, degeneracy pressure kicks in the core and halts the collapse before you get full-on proton-proton chain hydrogen fusion. And so you don't become a star. That's why you can't have stars less than about 80 Jupiter masses, because degeneracy pressure, which we'll talk about more when we talk about white dwarfs, kicks in and supports the core. That's what's the case in Jupiter now. The core has degeneracy pressure that keeps it from collapsing any further. Between 13 and 80 Jupiter masses, the core does get hot enough, like 1 million Kelvin, for deuterium fusion to occur for a little while. But deuterium is a rare isotope of hydrogen and is very easy to fuse. And so every star burns deuterium for a little while before it burns hydrogen. And I believe it was it Cecilia Payne-Kapowski? I can't remember. I think it might have been her who said that deuterium is therefore stellar baby food. It's like the first nuclear fuel that they eat, so to speak. If you have something which only goes to the baby food stage, it only fuses deuterium and never gets hot enough to fuse hydrogen, ordinary hydrogen, well then we say that it's not a star and it's also not a planet. It is you know what it would be in that case? It's a brown dwarf, we call it. A brown dwarf is an object between about 13 and 80 Jupiter masses. Its core gets hot enough to fuse deuterium for a while, but never hot enough to undergo the full proton-proton chain. So then you got a brown dwarf, and if you're below that, you're a planet instead. So Jupiter is not a brown dwarf because it would need to be about 13 times more massive than it is in order to have ever fused deuterium. Okay? Questions, comments, observations? All right, let's talk some more then. Let's put some math in all of this. Let's talk about the so-called Jeans criterion, which will tell us what is the minimum mass that a cloud needs to have given its internal pressure and temperature and density. What mass does it need to have in order to be unstable to gravitational collapse and form a protostar and then a star? This is named after the astronomer James Jeans, which I think is a great name. So let's talk about how this works. Way back in 1902, we came up with this. So, formation of protostars. He was knighted probably for this work, I'm not sure, so he was Sir James Jeans. I don't think it has anything to do with, pepper pants, but still. So, formation of protostars. The Jeans criterion. Sir James Jeans who lived from 1877 to 1946. In 1902, was the first to investigate the conditions necessary for an interstellar cloud to collapse. What's going to make gravity exceed pressure? So let's put that in there, right? Fundamentally, gravity must exceed pressure. Well, what's our favorite theorem in astrophysics? Starts with a V. The virial theorem. Yeah, the virial theorem raises its beautiful head and speaks to us again. Virial theorem. So useful. So, the equilibrium condition, remember, if a cloud's in equilibrium, it means that 2k plus u is 0, where k is its thermal kinetic energy, and u is its gravitational potential energy. Right? Remember that? Twice the thermal kinetic energy plus the gravitational potential energy for our cloud. If they add up to 0, right? U is minus 2k is one way to write the virial theorem. Pressure, it's in equilibrium, so it must be that's the condition where pressure and gravity are in balance, and the cloud is in equilibrium. We are fulfilling the virial condition. Pressure and gravity in balance. Cloud is in equilibrium. So let's look at the two cases where they are not adding up to 0. 2k plus u is not adding up to 0. If 2k plus u is greater than 0, let's see, first of all, k, positive or negative? It's the thermal kinetic energy, positive or negative? Is there such a thing as negative kinetic energy? No. So this is positive. What about the gravitational potential energy? Positive or negative?
Positive.
So negative. Womp womp. Now remember that if I had just two masses, right, big M, little m, distance r between them, remember that the gravitational potential energy is minus, do you remember the expression? What is it? Go ahead.
M1, M2, big G over
I call them big M, little m, so I'll say big M, little m, over
R.
R, and there's this important number to do with gravity that comes out in front here.
G.
Big G, yeah. Minus G, M, M. You did that on purpose, right? You're just so excited, you're like, ah, right. Yeah. Almost as excited as Kathleen earlier when I announced the homework. Yes.
Oh, yeah.
It's-
I'm still really excited.
I can see that, as a matter of fact. In fact, I keep seeing you're barely holding on to your writing titles. So, all right, so minus big G, big M, little m over R is the gravitational potential energy. Here we are setting the zero gravitational potential energy by definition is when they're how far apart? Infinitely far apart, right? R equals infinity corresponds to 0. Gravity is an attractive force, so that means that if you put them far apart and let go, they're going to start falling towards one another. They're starting with 0 in the limit of R going to infinity, but it was just really big. Essentially 0 gravitational potential energy. You let go, what's going to happen to their kinetic energies? If you let them go from rest, what do? They start falling towards one another, so what's happening to their kinetic energy? It's getting bigger and bigger. Their total energy, what did it start as if they were far apart from one another and at rest? What was their initial total energy? Kinetic plus potential. 0, right? Because they weren't moving, 0 kinetic energy. And they're far apart, so this is very large, so 0 potential energy for all intents and purposes. So we start them out with 0 energy far apart. You let go, the kinetic energy is becoming positive, so what has to be true about the gravitational potential energy to compensate? It's becoming negative. So this needs to be a minus sign right there. It has to be that if you let the 0 of energy be when they're very far apart, they have negative energy, negative potential energy when they're closer together, because if you let them go, they'll be turning gravitational potential energy into thermal energy. So the gravitational potential energy is decreasing from 0. It's becoming negative at the same time that the kinetic energy is becoming positive. So it's negative. Oh boy, burn that into your brain. The gravitational potential energy is negative, whereas this is positive. K is positive. So if 2k plus u is greater than 0, is this going to be the situation where it's like the thermal kinetic energy is winning, or where the gravitational potential energy is winning? Who's winning here? If 2k plus u equals 0 it's a tie, so to speak. Gravity and pressure are in a tie. Is this going to be the case where pressure is winning or where gravity is winning? The kinetic energy, the thermokinetic energy is tied to the pressure, right? So this is the term that's rooting for pressure, so to speak. This is the term that's rooting for gravity. If 2k plus u equals 0, it's a tie. 2k plus u is greater than 0. Who's winning?
Pressure.
Pressure is winning, right? Pressure is winning in this case. Pressure is winning. Here we're going to say the pressure gradient force, right, the dPdr force, pressure gradient exceeds gravity in in this case, pressure exceeds gravity. If you got a cloud where 2K plus U is greater than 0 and pressure exceeds gravity, is that cloud going to sit there? Is it going to shrink? Or is it going to expand? If pressure is winning, what's it going to do? Yeah, it's going to expand because pressure is winning. Pressure, outward pressure is stronger than gravity, so our cloud expands. Cloud expands. Are we forming a protostar in this case? If our cloud's expanding, are we making a protostar? No. A protostellar cloud starts out like maybe a light year across, and if it's getting bigger, it sure as heck ain't forming a star. So the condition where we will have that gravity's winning the battle will be 2K plus U is less than 0. 2K plus U is less than 0. In this case, pressure gradient is less than gravity. Cloud contracts. So that's what we want. 2K plus U has to be negative. It has to be less than 0 if we got ourselves a cloud that's forming a protostar, which means 2K plus U equals 0 is the limiting case. That's the limiting case where we're right on the border. K plus U equals 0 is the limiting case. So that's going to lead to our Jeans criterion, like to be at least on the borderline. You need 2K plus U to be 0. That'll tell us something about, well, when can we expect a protostar to form? As you will blank show in the homework, for a spherical cloud of uniform density, the density is constant within the cloud. Now, if it's collapsing, the overall density is increasing, but I mean it's not depending on position. For a spherical cloud of uniform density, just take that as a nice simple example. A spherical, real cloud's not going to be spherical, it's not going to be uniform density. Shh. We're just studying the basic ideas here. For a spherical braid, we always make approximations, right? Spherical cows, spherical clouds, right? Now, the spherical star approximation is a damn good one. The spherical cow approximation, not as good. The spherical interstellar cloud approximation is more like approximating a spherical cow, but we still learn interesting things from it. So, for a spherical cloud of uniform density, so we'll take this as a nice simple case. Uniform density, density doesn't depend on position. The gravitational PE gravitational potential energy is U equals minus 3/5 times G times the mass of the cloud squared divided by the radius of the cloud. So m is the mass of the cloud. Big RC, that's the radius of the cloud. So in the homework, you can do an integral. Imagine building the cloud one layer at a time, and you find out how much gravitational potential energy is associated with adding each layer of thickness dr, of mass dm to the cloud. You do an integral, and you get that the total gravitational potential energy is minus 3/5 g mass cloud squared over the radius of the cloud. If you've taken E and M, you almost certainly did something very similar to find, say, the electrostatic potential energy of a uniform ball of charge. This is the same problem mathematically because gravity is also an inverse square law force. And so you might find in your homework that Dr. Trees probably gave you, or an example from your E&M book of finding the electrostatic potential energy of a uniform ball of charge, and you just make the appropriate modifications to find the energy of a uniform sphere of mass. Figure out what its gravitational potential energy is. And of course, you know, I don't even really have to ask, but how will you show this in homework? Yes. Yes, joyfully, or maybe even incredibly joyfully. ASK, initials, okay? So, just ask. There you go, yes. Never thought of that one before. Okay. All right, anyway, hey, make all kinds of things with that. Yeah, what does Anushka think? We'll just ask her. So, anyway, okay. So, and you don't show this in the homework, it's just, so it's thermal kinetic energy. Here we're going to use the equipartition theorem. Its thermal kinetic energy is going to be K equals, so remember that in thermal equilibrium, each degree of freedom gets per particle half kT of thermal equilibrium kinetic energy. So that means that because the particles are moving in 3 dimensions, each particle gets 3/2 kT of average thermal energy. And if there's capital N particles, the total thermal energy is then 3/2 N kT. So the kinetic energy will be, thermal kinetic energy will be 3/2 capital N for the total number of particles, Boltzmann constant times the temperature. So N here is total number of particles. And since I'm running out of room, I'll continue that over here. So we got, well, that'll be 3/2 times the mass of the cloud divided by mu mh times kT, since mu mh is, so remember, what is mu? Not reduced mass in this case. Here I'm using mu to be the what are the syllables? Mu here is the Yes?
Mean mass of all the particles?
Almost. So mu itself is the mean molecular weight. Mean molecular weight. Just a reminder here. Mean molecular weight. And that is the average, well, the mean, because that's, you know, mean as an average, mean particle mass in terms of the mass of hydrogen, right? So in other words, the mean molecular weight is the average mass per particle divided by the mass of a hydrogen atom. So mu mh, so mu by its mu mh is the mean particle mass. That's the mean particle mass. So the mass of the cloud divided by the average mass of each particle in the cloud is the total number of particles in the cloud. That's why 3/2 capital N kT is 3/2 mass cloud over mu h kt because since mu h equals the mean particle mass because of how it's defined. So mu h is the mean particle mass, so the cloud's total mass divided by the average mass of the particle is the total number of particles in the cloud. So therefore, K, the cloud's thermal kinetic energy, is 3/2 mass of the cloud over mu h times kT. So now we can put in the borderline criterion that we were looking for. So for 2k plus u equals 0, that says that, well, for 2, let's put it this way. 2k plus u is less than 0. That was the criterion, right? We want 2kt plus u being less than 0 to get a collapse, says that 2k is less than the magnitude of u, because u itself is negative, so its absolute value is involved here. So if twice the thermal kinetic energy is less than u in magnitude, then u is bigger in magnitude, and so the gravitational potential return is winning. The cloud wants to collapse. So here's our criterion. 2k has to be less than the magnitude of u. Well, we know what u is, we know what k is, so we know what to write down. This says that 3 times the mass of the cloud times kT divided by mu mh should be less than, for our spherically symmetric uniform density cloud, 3/2 g mass of the cloud squared over the radius of the cloud. So our cloud needs this to be true in order to collapse. Questions? Does that make sense? What questions do you have? This is saying there's not enough thermal kinetic energy to produce enough pressure to counteract the gravity, is what this is saying. Now we're not done. But this is ultimately what we're going to come up with for the G's mass for the cloud is going to rely on this being true. It's going to be based on that being true. Questions, comments? Now use that the mass of the cloud is 4/3 pi times the density of the cloud times what? What else? I'm missing one factor in this. So if I take the density of the cloud times what will I get its mass? Density times what is mass? Volume. There's a 4/3 pi so far. What do I need to give me the volume of my spherical cloud? The volume of the sphere is 4/3 pi r cubed, right? R cube's got to be cubed because it's volume. You need the right units, meters cubed. So 4/3 pi rho cloud r cloud cubed. So rho cloud is the cloud density. To write that the radius of the cloud is 3 times the mass of the cloud divided by 4 pi times the density of the cloud, cube root to the 1/3 power. Right, so we're just solving for our cloud in that line above. And then we'll put that back into this equation right here, substitute for our cloud there. So now we can say that 3/5 times g times the mass of the cloud squared times 4 pi rho c over 3 mc to the 1/3 should be greater than 3 times the mass of the cloud times kT over mu mh. So I flipped the order, right? In other words, I took the t, I put the t side over here, and if I flip an inequality, the inequality goes with it, right? In other words, if 2 is less than 3, if I flip that around, 3 is greater than 2, right? So if I flip the terms in inequality around, the inequality sign follows the flip as well. And so here, I am dividing by the radius of the cloud, so that's why this is, you flip this over. 1 over our cloud is flip this over right there, okay? And since there's only 2 lines to go, I'm going to give you a couple of minutes of free education so that I don't be like, spend the first 5 minutes on what is this, Wednesday? Monday, 5 days from now. That's way too far in the future, right? So we'll finish this up now, okay? Right, so is everybody buying what I'm selling so far with this? So let's take this to the next line then. So let's isolate the mass of the cloud to the 2/3 power, because I've got mc over here. Divide, and I've just got mc. Divide through, I've got mc. mc over mc to the 1/3 is mc to the 2/3. So mass of the cloud to the 2/3 power should be greater than, move everything else to the other side, and that simplifies to 5 kT over g times mu times mh times 3 over 4 pi times the density of the cloud to the 1/3 power. Well, who wants a criterion in terms of what is the 2/3 power of the cloud's mass? So how do I undo that? What do I do to both sides to just leave this as mass cloud? Raise to the 3/2. Raise everything to the 3/2, because something to the 2/3 to the 3/2 is something to the 2/3 times 3/2, something to the 1. So raise to the 3/2, and this is what will get us the box. So the mass of the cloud should be greater than around, because we assume uniform density, we assumed it's a sphere, blah, blah, blah. So we say greater than around, since we made some simplifications. 5 kT over g mu mh to the 3/2 power, 3 over 4 pi rho cloud to the 1/2 power. And this by definition is capital M sub j, the gene's mass. Ta-da, this is what we were after. The gene's mass. So in other words, if you're told, well, this interstellar cloud has a certain temperature, and you know it's made of molecular hydrogen, so you figure out that its mean molecular weight is about 2, and you know how big the cloud is, and you've got an estimate of its mass, and so, I shouldn't say that. You know what the density of the cloud is from maybe how the radio waves from something like that. Plug this all in, and if your estimate of the cloud's mass is bigger than this, you expect that cloud to form a star, or it can start collapsing, and if it's less than that, it can't. So this is the gene's mass. This is one form of the gene's criterion. How massive does a cloud need to be given its temperature, density, and composition to collapse? And so if you think about it, well, if you have a given density, temperature, and composition, then the bigger the cloud is, does that make it more or less likely to be able to collapse? The bigger in radius it is. So in other words, a given clump of material, given temperature, composition, density, if I make it physically bigger, is that helping it be able to collapse or hindering it? Its mass needs to be greater than this expression. As I make the cloud bigger, and I'm assuming that if I'm keeping the same density, right? So in other words, it's the same density, the same temperature, the same composition. Compare two clouds of the same density, temperature, and composition. The bigger one in radius, would it have more mass or less mass? More. Is it more or less likely to have exceeded this criteria? More, right? So in other words, there's also a gene's radius as well. And so a bigger cloud of a given conditions is going to be more likely to be able to exceed the gene's mass and collapse small. So that's the gist of what genes discover, what it takes. And conversely, if I have a cloud of a given mass, and I compress it and I make it shrink, if I didn't change the temperature, that would make it more likely to collapse as well, because the density would go up, which would reduce the gene's mass, and so as a result, it would be more likely to collapse. A cloud of a given mass, if you compressed it and didn't change the temperature, you'd make it more likely to collapse. If it's changing the temperature as well, then you got to figure out which effect is bigger, the temperature change or the density change after you collapse. Okay, but typically when you get shock wave passing through, the density change is more important than the temperature change, and it makes it bigger. Okay, questions? You're welcome for the free education. I will not charge you. Go home and tell your parents you got some free education. They'll be so happy.